I think you all know this, but since I don't know what levels you're at, I'll start at the beginning. Nuclei have protons and neutrons in them, called nucleons. They're fermions. They have half-integer spins. Number of neutrons is called n, number of protons z, and the sum of them is a. Okay, you all know this, right? Everybody knows that? Okay, good. A given element, such as carbon or iron or tin or lead, has a fixed number of protons. In these cases, oh, geez. Okay, who sees a mistake there?
That's the atomic mass.
Somebody tell me the mistake.
Those aren't the number of protons.
In which element?
Carbon.
Yes, that should be 6. Okay? Okay, anyway, but they can have a variety of neutrons, and those are called isotopes. Okay. Nuclei with odd numbers of nucleons, either even z odd n or even n odd z, have half-integer total angular momentum because fermions have half-integers. Nuclei that are even in both or odd in both have integer spins. We'll focus most of our discussion on this, except for today, where we'll focus mostly on the motion of individual nucleons in the nucleus. And the nucleons interact with each other primarily by two forces, the strong and the electromagnetic force. Gravity comes in at a minuscule level, and the weak interaction comes in a very important way in processes such as beta decay, tests of the Standard Model, but doesn't affect so much the structure of nuclei. Okay, comment about the strengths of the strong and electromagnetic forces. The strong force, not surprisingly, is strong. And for example, in helium, strong force has a strength of tens of MeV, and the Coulomb repulsion of 2 protons is less than an MeV. So you might think, why don't we just ignore the Coulomb force? It's so weak. But that neglects an important point. The strong force is short range, and we will see in a few minutes how short it is. But it's shorter than the size of the nucleus. And that means that a nucleon in one side of the nucleus doesn't really see very much about what's going on the other side. And it only interacts with nucleons in its immediate vicinity. So that means that a given proton or neutron interacts with the strong force only with something like 10 other nucleons. So if there's a saturation, if there's a maximum in the number of nucleons that a given nucleon interacts with, that means the total number of strong interactions scales linearly with the total number of nucleons. If each nucleon interacts with 10 others and you have 10 nucleons, that's 100 interactions. If you have 20 nucleons, that's 200. If you have 50, that's 500. So it's linear. On the other hand, the Coulomb force is long range. And so that means that every proton interacts with every other proton in the nucleus. And so that means that the hell has happened here?
Maybe try clicking with the mouse.
With the mouse?
No, with
Touchpad.
the pad. Okay, and now click next.
Very good. How did you get so smart? Okay. Okay, so the strong force scales as the number of nucleons. The Coulomb force, though, all protons interact with all others, so it scales as z times z minus 1, which is like z squared. So for large enough z, the Coulomb force will eventually dominate. And you'll actually see that domination in about 30 seconds. The heaviest nuclei, those with z greater than about 104, in fact should not exist. The Coulomb force should keep them from existing. And we can discuss later why they exist. Okay. Here's the scope of nuclear structure physics. This is the nuclear chart. I guess you've all seen this. This is number of protons, number of neutrons. The black boxes are the stable nuclei. The yellow areas are nuclei that we know something about. The green area nuclei we know essentially nothing about. Okay. I don't like that. Okay. What do you notice about this plot? If you look carefully, from here to about here, the stable nuclei have equal numbers of protons and neutrons. And that reflects the fact that the nuclear force, the strong force, is the same for proton, proton, neutron, 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 proton. On the other hand, when you get to heavy nuclei, the stable ones have many, many more neutrons than protons. For example, lead-208 has 82 protons and 126 neutrons. And the reason for that is exactly what we just talked about, namely the competition between the strong force and the Coulomb force. Heavy nuclei need extra neutrons to buffer and keep the protons a little bit apart. Otherwise, they wouldn't be stable. Okay, now, there are 4 frontiers in this subject. Now, you might be a little puzzled by the numbering system. You know the joke about the mathematician who was explaining to his friend that there are 3 kinds of mathematicians: those who can count and those who can't. That's the end of the joke. Okay. Anyway, I can count, but I want to talk about these 3 first. So proton-rich nuclei. Those are nuclei over here, and they have mostly been studied. Okay, because we can get to those by using stable beams and stable targets. Neutron-rich nuclei. This is where most of the action will be in the future. That's out here. We can't get to these with stable beams and stable targets. We can get to them by studying exotic, well, they are exotic nuclei, by using accelerators that produce exotic nuclei. And that's one of the most exciting areas in nuclear physics today. The heaviest nuclei, those are the ones up here. These are the ones you see in the newspaper. When someone discovers Z equals 113 or Z equals 114 or Z equals 118, it makes a big headline in the New York Times or the equivalent European papers. And some of us, I mean, that's very important things. Those are important things to discover. Some of us wonder why nuclei. Now, the 4th frontier is not so obvious because it's like an internal frontier. Look here at the tin isotopes. There are about 10 or so stable tin isotopes. But the total number of tin isotopes that exists goes from all the way over here, all the way over to somewhere over there. We don't know exactly where. And so the evolution of structure within these boundaries is a very important frontier. We can study the structure of a nucleus like tin from 50 neutrons up to something like 130. And so we can see how the structure depends on changing the number of neutrons. Now, there are about 7,000 nuclei total. There are about 4,000 or so that we know nothing about. And nobody who has any intelligence at all wants to study all of them. That is stamp collecting. So we don't want to do that. But we view these unknown nuclei that we can now get to as a gene pool. We think of them as a set of nuclei with different properties, and we choose the ones we want that allow us to either isolate or amplify some specific physics. So basically we make designer nuclei. Okay? We don't want to study all of them, we pick the ones that tell us something special, or that we think will. Okay, this is another philosophy slide. Generally speaking, whenever you talk about any many-body system with lots of individuals in it, and this applies whether it's condensed matter systems, or nuclei, or clusters of galaxies, or groups of penguins, or different climatic things. Anytime you deal with a many-body system, there are usually 2 approaches to studying it. One is a microscopic approach, where you look at the behavior of the individual constituents. So, for example, the individual atoms in a crystal, the individual protons and neutrons in a nucleus, the individual penguins in Antarctica, and you look at how they interact with each other. That's a microscopic approach, and you try to understand the complex world of, in this case, nuclei from simple ingredients. namely nucleons and their interactions. And the question is, what is the force that binds nuclei, and why do nuclei do what they do? Now, it turns out that approach, when the number of bodies in the many-body system gets big, becomes essentially impossible. And so you are forced to look at another perspective. And it turns out that you actually learn things from this perspective that you can't learn from that, or it's difficult to. And so this is equally valuable in itself. It's the opposite. Instead of looking at the individual nucleons and their interactions, we take a few femtometer steps back from the nucleus and look at the thing as a whole, look at its shapes, look at its oscillations, look at the quantum numbers that describe this system as a whole, and try to see how all the complexity of all these interactions can lead to simple behavior. Okay, and we will find that nuclei exhibit incredibly simple patterns, and we want to see what they are and try to understand their origin. Okay, that's kind of the introduction. Is everybody with me so far? It's pretty simple so far, right? You knew all this, right? Okay. All right. Now we want to do some real nuclear physics. I want to talk about the structure of nuclei, how we can determine it, and what observable quantities, the technical word for this is observables, tell us what nuclei look like and how they behave. Nuclei are quantum mechanical systems. Any quantum mechanical system is going to have a ground state, and generally speaking will have excited states. And these states typically have some quantum numbers. Among other quantum numbers, they will have angular momentum and parity. For odd A nuclei, we're mostly just going to look at the ground state. For even nuclei, we'll consider several states. How's the temperature back there? Are you all miserable?
Back here is fine.
Back there, it's fine. How is it up front? It's fine. Okay. It's awful up here. Okay. All right. So I want to just, for even nuclei, I want to tell you what observables we'll look at. I probably should have had this slide later because I'm first going to talk about odd nuclei. But nuclei have a ground state, which is usually said to be at zero energy. And then they have excited states. And here I've just made up an imaginary nucleus to show you a couple of things. So here's the first excited state at 400 kilovolts. So I'm just introducing you to the fact that that's the energy scale. 1,000 kilovolts, another state, another one maybe at 1,400. Each of these states has an angular momentum and parity called capital J, I. Ground state of all even nuclei is always 0 plus. Who knows why that is? Why are the ground states of all even nuclei 0 plus? Anybody know?
So there are even numbers of neutrons and protons that cancel each other.
So why 0 plus? Why not 2 plus?
There's no angular momentum.
No? Okay, by tomorrow you'll know. Okay? First excited state of almost all nuclei, even nuclei, is 2 plus. Second excited state about 98% of the time is 4 plus, and so on. This ratio, the ratio of the energy of the 4 plus to the 2 plus, in this case 1,000 over 400, is a very important quantity. Another important quantity are the masses of nuclei, and the reason for that is that if there were no interactions between the nucleons, the masses would just be the sum of the masses of the protons and neutrons. But they interact, and we have E equals mc squared, so some of that mass gets converted into binding energy. And so the masses can tell us about all of the interactions of all of the nucleons in the nucleus. So if we do clever things with the masses, we can learn a lot. And then, I'm not really going to talk about this, but I'll just introduce it. Excited states don't live forever, they decay. And usually in an even nucleus, this will be a gamma ray, which will de-excite this level to this and this to this. Those gamma rays, their strength, or the lifetime of the levels, are proportional to squares of nuclear matrix called BE2 values. So I will occasionally refer to BE2 values. BE2, 21 to 01 means the square of this matrix elements from the first 2 plus state to the first 0 plus state. That's the notation. Okay. Masses. Let's see what we can learn about nuclei from some simple ideas about masses. As I said, they reflect all interactions. Now, the mass of a nucleus, roughly speaking, is the sum of the masses of the protons and neutrons. A proton-neutron weighs about a GeV, right? Mass of a proton is 931 MeV or so. Call that a GeV. So the total mass of a nucleus with a couple of hundred particles in it, is that for me?
Yeah.
Thank you.
Welcome.
So you've contributed 2 things already. Okay. The mass of a nucleus with a couple hundred nucleons is a couple of hundred GeV. The binding energy of a given nucleon is about 8 MeV. So it's not so easy to tell effects of 8 MeV when you're dealing with numbers of 200 GeV. So nobody really looks very much at masses. They look at things like mass differences, separation energies. And that can tell us about shell structure, phase transitions, collectivity. A very important thing you can do is go the next step and look at double differences of masses. And that's a very powerful technique that allows you to actually isolate specific interactions and understand how they contribute to structure. Okay, you can learn about the properties of nuclear forces by measuring masses very crudely, just even to 100 MeV. If you want to learn about shell structure, you need to measure them to MeV or a little bit better. If you want to learn about phase transitions, that's nuclei that change shape, you need to measure them to a couple of hundred kilovolts. If you want to look at collective effects, the same thing. If you want to study these interaction filters, you need to measure masses to 10 to 15 kilovolts. Now we're getting into the area of Isolde with isol trap. And if you want to study fundamental interactions, you need to measure them to less than a kilovolt. And that gets to be a little bit challenging, but can be done. Okay, I want to look at the very simplest plot you can possibly make and ask what it tells us. And I know Magda showed this plot, but I don't think she did what I'm going to do with it. So this is the binding energy of nuclei. Here's the mass number. And it's the binding energy divided by the number of nucleons. So it's the binding energy per nucleon. And it has a very characteristic behavior. It starts up like this, sort of linearly, and then at a mass of about 15 or 16 or 20, it becomes effectively constant. Okay, yeah, it drops off, but basically we can think of it as up, over. And what does that tell us? Well, let's make a simple model. I'm going to make the most crude, silly, simple model you can imagine and see what it tells us about the nuclear force. Let's assume that each nucleon, I'm going to show a table over here which will look a little complicated. So I'm going to go through it slowly. Let's assume that each nucleon interacts with n other nucleons. And we're going to change n and look at different cases for n equals 2, 3, infinity, and so on. And let's assume that all those interactions are equal. Now that's not true, but we'll just assume it. And let's look at what you would get for the binding as a function of n and a, and compare it to that data plot we just saw. So this is what we want to compare it to, up and over. Okay, so let's assume, first of all, that each nucleon interacts with all other nucleons. Okay, there are A nucleons in the nucleus. If each nucleon interacts with all others, the total number of interactions will be A times A minus 1 over 2. Right? If I now calculate binding energy divided by the number of nucleons, that goes as A minus 1. So if each nucleon interacts with all others, then the binding energy per nucleon should look like that. Does that look like the plot I showed you? Yes? No?
No.
Does it look like any part of the plot?
Yes.
So maybe there's something to it, but it's not quite right. Let's go to the other extreme. Let's assume each nucleon interacts, so that's this column. Let's assume that each nucleon interacts with 2 others. So how many interactions do we have? If we have 3 nucleons, then this one interacts with this and this interacts with this and this interacts with this and this. We have 3 interactions, 3 nucleons, 1 interaction per nucleon. Okay?
So what do you mean by interaction? You're talking about
Some sort of force between them, contributing to the binding. The strong force is attractive, and so the more nucleons it interacts with, the more pound it will be.
Okay. So attractive interaction.
Yeah, attractive interaction. Think of an interaction as giving some binding.
Yeah. No, sorry. No, any functional shape of the.
No. This is a very simple model, and you'll see how amazingly good it is.
Mm-hmm.
Okay, so if we have 4 nucleons, and each one interacts with 2 others, this one will interact with these 2, this with these 2, this with these 2, this with these 2. That's 1, 2, 3, 4 interactions, 4 nucleons. What about if we have 6 nucleons? This will interact with these 2, and so on. You have 1, 2, 3, 4, 5, 6 interactions divided by 6 nucleons. That's 1. So if each nucleon interacts only with 2 others, then if we divide the binding energy by the number of nucleons, we're going to have here 8 interactions, 8 nucleons, 6, 6, 5, 5, and so on. We're going to get a line which will look like that. Clear? Number of interactions is just equal to the number of nucleons. When we divide by the number of nucleons, we get a constant. Does that look like the plot we saw from the data? No? Yes?
Second part.
Does it look like part of it? Okay, so now we've got something that gives an upward part and something that gives a horizontal part. Let's try to combine them. Suppose we take the case where each nucleon can interact with 5 others. Okay, if you only have 3, you're going to get the same result you got there. Okay? And so you're going to have 3 interactions, 3 nucleons. Number of interactions per nucleon is 1. If you have 4 nucleons, then each one can interact with all 3 of the others. And you have 1, 2, 3, 4, 5, 6 interactions, 4 nucleons, that's 1.5 nucleons. And you took all the interactions and divide by 6, you get 2.5. And you get 2.5 here, and so on. And so that looks like this. This is the case if each nucleon interacts with 5 others. This is beginning to look like the plot we saw on the previous slide. Right? Now the previous slide, sorry about this. Previous slide started saturating around 12 or so nucleons. So you can pretty easily convince yourself, although you wouldn't want to actually draw these drawings, that if each nucleon interacts with 10 to 15 other nucleons, you will reproduce that plot. You'll have a steep section when you have less than 15 nucleons, and then it'll go constant. And so what this tells us, this trivial simple model, is, oh, I forgot that. Is that each nucleon interacts with 10 or so others. No, don't quibble about 10 or 15. I mean, it's a few others. And that means that the nuclear force is effectively short range, shorter than the size of heavy nuclei. I used that earlier when we looked at the chart of the nuclides to explain the equal numbers of protons and neutrons at the beginning, and this is the curvature. Okay, and you get this just by measuring the masses. Okay, this is called the saturation of nuclear forces. It also tells you, if you think about it for a bit, that the nuclear density is constant. Okay. Now, I'll do a little more with masses. I don't like this. Okay. I want to look at separation energies. That's the energy to remove 2 nucleons, 2 neutrons. And I want to show you in a highly technical quantum mechanical way rigorously what that looks like. Looks like that. Okay? There they go. Everybody see that? Okay. I'm going to bring them back. Okay. This is the data. This is the data on 2 neutron separation energies from tellurium up to, from 52 neutrons up to 132, and from tin to lead. And what do you see here? Does this look complicated? Does it look simple? What do you see?
Yeah, the colors.
The colors.
Yeah.
You see any patterns? You see any irregularities? Let me tell you what you should see. Okay, you see the most striking thing are these sudden drops. Okay? And you'll notice that you have these essentially linear segments, in this case up to n equals 82, and then the nucleus with 84 neutrons suddenly has much lower binding energy, much lower separation energy. Same thing happens at lead, 126, 128. Okay? And that tells us that somehow nuclei with 2 more neutrons than some special number are somehow much more weakly bound. Okay? The explanation, which we'll see in a while, will be that when you get past n equals 82 and you add 2 more neutrons to get to n equals 84, they have to go into an outer shell. These represent the orbits of the nucleons. And this outer shell is much less bound than the inner shell. Okay? This will tell us about magic numbers and shell structure. Okay, what else do you see? You see this flattening here. This is a very subtle thing which we won't actually discuss in these lectures, although we can if you want. This is evidence. Notice what you have here. You have linear trends and then suddenly a flattening. If I continue this linear trend, that means that these nuclei are more, the separation energy is larger than what it would have been if something hadn't happened. So these nuclei have greater binding of the last nucleons than they would have. And that greater binding is due to their having changed structure, in this case gone from spherical to ellipsoidal, and they gained energy in doing that. So changes like this can signal major changes in structure. The other thing you see, the most obvious thing, is these linear segments. Okay? So basically, as you add neutrons, the neutrons just become less and less bound because they keep filling orbits that are further away, and it's easier to pull them out to infinity. If you look carefully at this, if I put this red ellipse on this, you would notice these curvatures. Those curvatures are due to what are called collective effects, and you can use data like this to understand some of that collective business. Okay, that is masses. I now want to look at spectroscopic observables. By that I mean things having to do with the energies of specific states. So here's a plot of the energy of the first 2+ state in all even nuclei. And what do you notice? Well, first of all, you notice some red here, which is simply a mistake. I meant to have it be black. The second thing you notice are these spikes. Okay? Let me go back to the masses for a second. So what we've learned from here is that there are certain numbers of neutrons, 82 and 126, that have special significance. Somehow nuclei change their behavior when you go beyond those numbers. And if I had shown you this data for the entire nuclear chart, you would see other numbers. And some of those other numbers are 2, 8, 20, 28, 40, 50, 82, and so on. So what you see is that the first 2+ state jumps in energy very dramatically when the number of neutrons reaches a specific number. And after that, it falls off rather rapidly. So those are the 2 obvious features. These high values occur at these special numbers. So somehow the nucleus is very rigid to excitation when you have those numbers of nucleons. These numbers are called the magic numbers. Who knows about magic numbers of nuclei? Raise your hand if you know about magic numbers. Raise them very, very high so I can see. Good. Who knows all about the independent particle model? Oh, the number dropped. Okay, good. Okay, so then think of this as review. Okay, here is a blow-up of this section just to show you how beautifully regular and smooth it is. Now, this should amaze you. Now, it probably didn't amaze you, but it should. They do 10 to the 21 orbits per second. And so you would think you would have complete chaos. But you don't. The patterns are very regular. Okay, that's one of the amazing things about nuclei. Okay, now I want to talk about this other observable, R42. How does it vary? Why does it vary, and why do we care? The last one is the easiest. We care because it's almost the only observable that immediately tells us something. So let me come back to the 2+ and just illustrate that. If I talk about a 2+ energy of 1.5 MeV, okay, so that would be here. I can't tell you much about the structure because 1.5 MeV here occurs between magic numbers, whereas 1.5 MeV here is about at a magic number. Okay, so the absolute value doesn't tell you anything. You have to know which mass region you're in. On the other hand, with R42, the value tells you something immediately. It's also easy to measure, and it reflects the development of collectivity. Collectivity means that nucleons going around the nucleus are showing correlated motions and interacting with each other in a way that develops correlations. There are 3 special cases for R42. Values less than 2, values about 2, and values about 3.33. Does anyone know what these 3 limits correspond to physically in terms of what the nucleus is doing? Yes?
Well, okay, so the 3.3 is rigid rotor case. The around 2 is the vibrator case. And below 2, I think, is a single particle excitation.
Does anybody else know that? Who else knew that? You can all raise your hands because you can repeat it and look very knowledgeable. Okay, so you knew it. Sort of. Okay. Okay. Well, you're right. Almost right. You weren't quite right on that, but almost right. Okay, but I want to show you the data without biasing you by telling you what it means. So here are nuclei with 2 valence nucleons. So not single particle, but 2 particles.
Okay.
And they have spectra independent of the mass region that look remarkably similar. They all have a 0+ ground state. They all have a first excited 2+ state. And they have a sequence of states that goes monotonically in spin. 2, 4, 6, 8, 2, 4, 6, 2, 4, 6, 8. And the jump from the ground state to the 2+ state is bigger than the jump between the 2 and the 4. That means R42 is less than 2. This is a characteristic value when you have a nucleus which has a magic number of protons, a magic number of neutrons, and 2 more particles of one type. So we call those 2 valence nuclei. Okay? You see it all throughout the nuclear chart. What happens when we start from a doubly magic nuclei, increase the number of valence protons and neutrons? Let's look at a case with a few valence nucleons. So here is tellurium-134. It has 82 protons, which is a magic number, 52 neutrons, which is in correspondingly for R42. If I superimpose the magic numbers on that, you can see that you get exactly the patterns we're talking about. High 2+ states at the magic numbers, low R42s at the magic numbers, low 2+ states, R42s near 3.33. Okay? Understanding this is what when I talked about complexity and simplicity, this is one of the most regular and simple patterns that nuclei exhibit. And we need ultimately to understand this microscopically. We also need to find out if whether these patterns persist far up stability. And we'll see that they don't necessarily. Okay, this is all I want you to memorize for these lectures. It'd be good if you know these magic numbers and if you remember those 2 or 3 R42 values. I'm going to skip over this more or less. This shows BE2 values, basically the squares of matrix elements from 2+ to 0+. They also show very regular patterns, small values near closed shells, large values in the middle of the shells. That's again a manifestation of collective or coherent motion of many nucleons. Okay. One thing that's a very powerful approach is to plot not a given observable against neutron number, proton number, or A, but to plot a given observable against another observable. Okay, and I'll give you an example of that. And you can do a lot with this, but I'm just going to show you this just to introduce the idea. This is the energy of the first 4+ state in nucleus of this guy, from strontium to lead. And what you see is a very complicated pattern. For a given neutron number, you can have all sorts of values. You see some trends, but clearly it's a complicated picture. Now what I'm going to do is take that same data, and instead of plotting this against neutron number, I'm going to plot it against the energy of the 2+ state. And what you will see is that. It's the same data. It all falls on a bilinear line. The first part of this line has a slope. These are least squares fitted slopes of 3.33, and this is 2.00. You should recognize those numbers by now. And the only possible reaction to seeing this plot, and I hope you all had this reaction, but I didn't quite hear it, is...
Whoa.
What?
Whoa.
You got it! I mean, it's just astonishing. Now, whenever you look at a correlation of observables, or of any two things, you always have to ask, is it a real correlation or is it fake? For example, in the United States, it's been noted that when the American League baseball team wins the World Series, and it's an election year, the Democratic candidate wins. That's a false correlation. It's just accidental. And the reason these accidental correlations occur is because you have hundreds of thousands of things you can correlate with hundreds of thousands of things, and eventually you'll get one right. Okay, so I want to show you an example of a false correlation.